To power a modern grid, electrical substations must push millions of watts across vast distances. The central engineering problem is moving that energy efficiently without losing it to destructive heat along the way. The solution relies on the electrical transformer. It is a static machine with no moving parts or friction. Instead, it utilizes mutual inductance to transfer power between two isolated circuits. Its function is to step voltage levels up or down. But to maintain the exact same power and frequency from input to output, it must proportionally scale the current in the opposite direction. High voltage means low current, and vice versa. This physical feat, pioneered by Michael Faraday, relies entirely on invisible alternating magnetic fields linking two separate coils of wire, which presents a serious challenge. How do engineers mathematically model a machine that relies on volatile, invisible magnetic fields to solve real-world power distribution? To calculate the physical realities and energy losses of an actual transformer, we must first construct an impossibly perfect mathematical baseline, an ideal transformer. This diagram represents an ideal transformer at no load. On the input side, we have the AC source V1, induced EMF E1, and a small no-load current, I0. On the output side, an open circuit means the secondary current, I2, is exactly 0. The magnetic flux hits peak amplitude in 1/4 of a cycle, or T/4. Translating time to frequency yields the average rate of change. Multiplying by the 1.11 form factor gives the final RMS baseline, 4.44 times frequency times maximum flux. Finally, we multiply this base value by the specific number of turns on each coil to find the total induced voltage, E1 for the primary winding and E2 for the secondary. This establishes the voltage transformation ratio, defined by the constant K. K is the ratio of secondary turns to primary turns, which is mathematically equivalent to the ratio of their respective voltages. Because an ideal transformer is perfectly efficient, input volt-amperes must perfectly match output volt-amperes. Therefore, the currents scale in the exact inverse ratio. This perfect mathematical ratio is the theoretical heart of the machine, but it completely ignores the harsh thermal and magnetic constraints of the physical world. Real transformers are wound with thousands of feet of copper, and real wire inherently resists electron flow. This creates copper losses, or Joule losses. Both the primary and secondary windings possess a non-zero resistance. As current flows, that resistance generates waste heat, proportional to the current squared times the resistance. Beyond the resistance of the wire, we must account for magnetic leakage. In a physical machine, magnetic fields cannot be perfectly contained within the iron core. Some of the flux breaks away. This escaping leakage flux loops through the air and links only with its own winding. It contributes nothing to energy transfer, but produces a localized, self-induced EMF that chokes the current. To map this onto a schematic, engineers model these physical flux losses as inductive choker coils, X1 and X2, in series with the windings. The combination of the copper's physical resistance and the core's leakage reactance gives us the total primary and secondary impedance. In practical manufacturing, engineers mitigate these massive leakage losses by tightly interleaving and sectionalizing the primary and secondary windings directly over each other. Before a single watt of power is actively transferred to the secondary circuit, the system's total energy is already taxed by the physical resistance of the wire and the escaping magnetic fields. The electrical wiring is only half the physical structure. The heavy iron core itself introduces an entirely different class of energy loss. These are known as core losses, or iron losses. They occur strictly because the alternating magnetic flux reacts with the metallic properties of the core. The first component is hysteresis loss. As the alternating current oscillates, the iron molecules inside the core are forced to constantly reverse their magnetic alignment 50 or 60 times every second. That rapid physical friction wastes energy as heat. This phenomenon was mathematically defined by Charles Proteus Steinmetz. His formula shows that hysteresis loss relies heavily on the total volume of the iron and the maximum flux density. The second component is eddy current loss. The alternating flux induces its own localized swirling currents within the iron core. These tiny currents generate additional Joule heating, and they scale exactly proportional to the square of the applied voltage. Engineers model these core phenomena by adding a parallel magnetizing branch. Since iron losses depend on applied voltage, not load current, this branch is shunted across the primary, drawing constant power as long as supply voltage is maintained. The massive iron core draws a constant no-load current just to maintain the magnetic conditions required for power transfer. Calculating values using this complete equivalent circuit is mathematically tedious because the primary and secondary parameters are physically separated by the core's magnetic barrier. To simplify the math, engineers use an impedance reflection technique. We can virtually bypass the core by transferring the secondary resistance and reactance over to the primary side. To maintain electrical accuracy, these transferred values must be multiplied by the inverse square of the transformation ratio. Secondary resistance becomes R2 over K squared, merging with the primary resistance to form a single lumped equivalent resistance. This lumped internal impedance is the direct cause of the most critical metric in power delivery, the total voltage drop when the system is placed under physical load. This is defined as voltage regulation. It is the exact mathematical difference between the terminal voltage when the system is running at no load versus when it is operating at full load. As this equation shows, voltage regulation is always expressed as a percentage of the full load terminal voltage. Voltage regulation is the ultimate scorecard. It quantifies exactly how much the internal physics and thermal resistance of the machine degrade its theoretical ideal output. This presents a final engineering dilemma. How do you accurately measure these internal resistances and reactances in a sealed physical transformer without subjecting it to a dangerous full load operation? The solution is the short circuit test. The secondary terminals are deliberately shorted together, and an incredibly low, highly controlled voltage is applied to the primary side. The logic of the test is elegant. Because the applied voltage is barely above zero, the voltage-dependent core losses drop to a fraction of a percent. Mathematically, they can be completely ignored. Because of this, any power recorded by the wattmeter during the test is strictly the current-dependent copper loss. This allows engineers to perfectly isolate and calculate the transformer's equivalent resistance. This isolation explains why transformers are rated in volt-amperes, or kVA, rather than watts. Watts measure useful power delivered to a load, a value that shifts based on the load's power factor, which is an external variable the transformer cannot control. However, the machine's internal heat is generated strictly by voltage and amperage. Rating in kVA ensures the machine stays within its thermal limits, regardless of whether the connected load is resistive, inductive, or capacitive. The transformer cares only about its own internal physical limits.
Thank you for viewing. So far, if it gives you some information, hit the like button and subscribe for more such technical learning.